In the first part of this unit, we looked at uniform probability distributions, where every trial in a experiment or event had an equal likelihood of occurring. Now we're going to be looking at binomial distributions. For such distributions, all the trials are independent and only have two possible outcomes, success or failure. The probability of success is the same in every trial. The outcome of one trial does not affect the probabilities of any of the later trials, since they are independent. Now here's a fun fact. Repeated independent trials, measured in terms of such successes or failures, just like in the binomial distributions, are sometimes referred to as Bernoulli trials, named after the famous Swiss mathematician Jacob Bernoulli, who published many papers on logic, algebra, geometry, calculus, and of course probability. Now let's do this. In a binomial distribution, you find the probability of an event occurring x number of times after n independent trials. So here's our equation that we're going to use. X is going to signify the number of events. P is going to be your probability of success on a single trial. I'm just going to skip to Q over here. So Q is your probability of failure. So obviously your failure, since success plus failure is going to be 100%, so your failure rate is going to be 1 minus P. So 1 minus your success. And then N, choose X. Here's just the formula for N choose X. So N factorial over N minus X factorial times X factorial. Okay, let's do an example. Oh, and I'll come back to expected value, but expected value is just N times P. Should also mention that P and Q are consistent throughout because your trials are independent, so therefore they have a consistent probability, like a success and failure rate throughout the entire experiment. So looking at example 1, we want to find the probability of rolling a 4 3 times in 5 tries. Okay, so now let's label all our variables. So X is the number of events that we want to examine. So in this case, we want to figure out how many times we're rolling a 4 3 times in 5 total tries. So X is going to be your 3, and N is 5. That's your total number of trials. And your success rate, so P, is going to be 1/6, and we're looking at every single trial independently. So every single time you roll dice, you have 1/6 probability of rolling a 5. And so your failure rate is 5/6. Now plugging in those numbers, we get P of X, which is P of 3, 5 choose 3, P is 1/6 to the power of X, which is 3, times Q, so 5/6 to the power of N minus X, so 5 minus 3, which is 2. And notice that 3 plus 2 should add up to 5, so N minus X should add up to N, obviously. And this comes to 10 times 25 over 36. Remember that the exponent applies to the numerator and the denominator. And 1 out of 216, which is 125 over 3,888, which equals 3.2%. And that seems realistic because you're putting restrictions and they're pretty specific. So obviously if your probability of rolling just a single 5 is going to be 0.2, so 20%, then rolling 3 times in 5 tries is going to be significantly less. Looking at B, it asks how many times would you expect to roll a 4 in 5 tries. So now whenever you see the word expect, you're thinking expected value. So we're going to use our expected value, which in this case for a binomial distribution is n times p. So our expected value in this case is going to be 5 times 1/6, which is 5/6. So just as a reminder, your expected value in a binomial distribution represents the number of successes you would expect in n number of independent trials. So in this case, you would expect to roll a 4 not even once in five tries, since your expected value is 5 out of 6, which is not even 1. Now let's go on to our second example. A little bit more complicated. Find the probability distribution for the number of goals scored from 3 shots if the probability of scoring a goal on any given shot is 10%. Now, when it asks you for a probability distribution as opposed to a probability, you're looking for every single possible probability outcome. So you get a range of answers, not just one. Okay, so first thing we want to label our variables. So we know that we're just looking at 3 shots. So that's going to be your n number of trials. And in terms of x, you want the entire probability distributions. So we're going to look at 0, 1, 2, 3. So from all possible trials until the 3rd trial. And then we know that your probability of scoring is 10%, so 0.1, and so therefore your failure rate is 0.9, 90%. So I made this chart to list our probability distributions. So x is representing your number of shots, and so our distribution is going to include 0, 1, 2, and 3, because we're just looking for all possibilities in the first 3 shots. And then your probability is going to be, according to the equation, 3 choose x, so n choose x, times what's your success rate, 0.1, to the power of x, which is 0, times 0.9, your failure, and 3 minus 0 is 3. So for same thing for the first shot, so 0.1, now your exponent is 1, and 3 minus 1 is 2. 3 choose 2, 0.1 squared, and then 3 minus 2 is 1, and 3 choose 3, 0.1 cubed, it's x, and 0.9, 3 minus 3 is 0. And just to evaluate these, we know that 3 choose 0 is 1. Anything to the power of 0 is also going to be 1. So this is 1, this is 1, so we're just really calculating 0.9 cubed, which comes out to 0.729. So here are our solutions, and now we want to graph our values. For x, when x is equal to 0, it's actually going to be off the charts, so I'm just going to get as high as I can. When x equals 1, it goes to a little over almost 2.25. And then for 2, it's 0.027, so that. And 3, it's even less. So as you can see, there's a huge decrease in probability as you increase. So your highest probability is even before you take a shot. That's your highest chances of scoring. And a key thing to notice here is if you add up your probabilities, you are going to get 100%, so 1. and that should always work out because this is basically the probability breakdown for each trial in your experiment. Now looking at part B, how many goals would you expect to score on 3 shots? So your expected value is n times p. In this case, n is equal to 3, and your probability of success is 0.1, which comes out to 0.3. So how do we interpret that result? Basically means that you would expect to score 0.3 times or not even once in 3 shots.